So, hi everyone. So, we're continuing our discussion on lesson 1.2 estimation graphs and mathematical models, and this time we will be focusing on graphs. Okay, so I am pretty sure that you have encountered different types of graphs in your earlier math classes. You've had circle graphs or pie graphs, line graphs, and also bar graphs. Okay, so those are what we will be working on for this lesson. So this is an example, as you can see, of a pie graph. So in this scenario, we have a number that is given to us by the U.S. Census Bureau, which was available in 2012, that the population of Americans 20 years or older is 229,937,770. Now, those people, they were asked about the definition of old age, and based on the result, this is the representation of how many of them pretty much defined old age. So as you can see, looking at how our circle or pie graph was cut into pieces, a big chunk says that old age is a decline in physical activity. Around 32% says it's a decline in mental functioning, and then the others says it is reaching a specific age, retirement, becoming a grandparent, and some of them even say they don't know what is old age. So looking at these numbers, we have two scenarios that we have to consider here. So we are looking for a calculation that shows the number of Americans 20 years and older who defined old age by the decline of physical ability. So if we are going to refer to this chart, the decline of physical activity is right over here, and we are looking at 41%. Okay, so here it is asking for a calculation. So when we look for the actual value, so we are going to be looking at the actual value, so that would be 41%. Now remember, multiplying percents, you change them into decimals. So 41% is going to be 0.41. And then you multiply that with the actual population. And so the given population is 229,937,770. Oops, sorry, my bad. This is a 7. Okay, 770. So if you use your calculator, okay, if you use the calculator, do this multiplication, you will end up getting 94,274,486. So this is the exact number of Americans 20 years old or 20 years or older that thinks or believes that old age is about the decline of physical ability. Now, the second part of this problem is that we need to make an estimated answer, meaning, as you can see, looking at these numbers, it's like so crazy. Like you have different digits. It's so freaking. It's pretty difficult to even say the whole number itself. So we're gonna look for an estimated value. So when we talk about an estimated answer, we're gonna use our rounding skills. Okay, so 41%. Can we round it up to a whole number? I mean, a better whole number. So 41%, we can say, okay, let's use an estimate of 40% instead of 41, right? And then for the population, you have 229 million, blah, 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 okay? We can simply round it up to the nearest 10 million. We can change this so that it would be just, this is a rounded value and all of this will be 0, okay? So in our case, our 41% will now change to a 0.4, okay? That's our estimated value for the percent value. And then if we round our original number for the population, if we round off and make this in the nearest 10 millions, we're looking at the digit 2, and then we gotta look at the neighbor digit. It happens to be 9. So is 2 gonna stay or will it increase? 9 is higher than 5, and so this 2 will now change to a 3, and then the rest of these digits will be replaced by zeros. So, okay, so this is our estimated values for each of these given numbers. And if you look at it, if you do your multiplication on your calculator, zero point 0.4 times 230 million, that is around 92 million. Okay? Now, taking a look, is 92 million near a decent value compared to 94,274,486? This is a pretty much near estimate. Thinking about, we're talking about millions of people. So it would be a quicker computation, a quicker estimation if we can round our percentages and even the population included in this problem. Okay? Now, this time, we'll be working with bar graphs. So bar graphs, so from the name itself, bar, you would be seeing quantities or numbers being represented by vertical graphs, vertical bars or horizontal bars, and then we can also use those bar graphs to make some predictions. So let's take a look at this scenario here. So as you can see from this bar graphs, we have two colors, red and yellow. The red bars represents the life expectancy of males in the USA. So when we say life expectancy, that's the pretty much how long a person can live. So on the average, around 1950, a typical man can probably reach up to 65 years old. So it's very rare for them to reach 70, 80, 90, okay? So that's that. So in this problem, what are we going to focus on? The red bar or the yellow bar? The question is asking about the estimate of a man's increased life expectancy rounded to the nearest hundredth of a year for each future birth year. Okay, so it was specifically mentioned that we have to look at the man's increased life expectancy, which means we will focus on the red bars. Okay, now for us to be able to make an estimate for that, okay, you will see that every 10 years, you will notice that the life expectancy has been increasing, correct? So what we will do is we will find the difference, okay, the difference of life expectancy, okay, divide it by the total number of years, total years, wherein that change happened, okay? Now, for us to find the difference of the life expectancy, we need to subtract the highest or the latest value with the oldest value. Okay, so in this case, our latest life expectancy value is 76.2. We will subtract it with the earliest, the oldest value, which was 65.6. Okay, so that is the difference of the life expectancy. Now, for how long did that increase happen? Well, we need to know how many years was it between 2010. So we can subtract 2010 by the original year where they started the data, which is 1950. Okay? So if you do your calculations, you will be getting a 10.6 if you subtract the upper part, the numerator, and then 2010 minus 1950, that's a total of 60 years. And so if you divide 10.6 by 60, we have an average of 0.18 years. Okay, 0.18 years. That's the change. 0.18. Let's say if you're gonna change it into months, you multiply that by 12. Okay, so pretty much that's the increase that's happening every year based on the data that we are given in this graph. Okay, so how can we use this value? Now, we can use that pattern. So we can say that every year there is an expected 0.18 increase in the age the life expectancy of men. So how can we predict the possible value, the possible life expectancy age of a man who is born in 2020? Now you can see our data is until 2010 only. So how much will it be on 2020? All right. So for us to be able to get that value, what we need to do is we find the original value, the starting value. So basically, the initial value or the start initial value plus we add how much change does it happen every year. Based from our computation earlier, there is an increase of 0.18 every year. Now the question is, how many years is it going to be for 2020? So we know that we need to get the difference between the desired year and the original or the initial year of data. So here, we will multiply it by the total years. Okay, so pretty much that's the pattern that we will do. So what is our initial life expectancy? It was originally 65.6 plus every year it increases by 0.18. Now, how many years did the increase happen? So 2020 minus 1950, that is actually a total of 70 years. Okay, so 70 is 2020 minus 1950. That's why we got the 70. So you can plug in this value on your calculator. This is going to be, so 65.6 plus, if you get the product of 0.18 and 70, that is going to be 12.6. So adding this two, we are possibly looking at 78.2 years old. That is the expected life, that is the predicted life expectancy of a man by the year 2020. Okay? So that's how we can use bar graphs to interpret these values. Line graphs, as you can see, they are made of lines. Just like in a bar graph, you have some representation for your vertical and your horizontal axis. What I really like about line graphs is I think they are much more pretty much direct, especially when answering some questions, okay? So here, find an estimate for the percentage of seniors who smoked cigarettes in 1995. So how are we going to find this number? So we need to look at 1995, which is this year. Now, which do we have to consider? Is it the alcohol or cigarettes? According to the problem, it has to be cigarettes. So we're going to look at the purplish, reddish graph. And in 1995, this is that point. Oops, sorry. This is that point here. So if you're going to analyze this, let me try that over here, is somewhere here. So looking at the location of this point, we see that that is between 30% and 40%. If you analyze, is it higher than the half? Pretty much no, if you look at it closely. So our estimate would be a good 33% or probably 34%. If you say 36 or 37, it's not going to be believable because as you can see, the point is below the half of 40 and 30. Okay? Next, in which 5-year period did the percentage of seniors decrease the greatest rate? So again, we're talking about the cigarettes, so it's gonna be the red. Looking here, so this is down, 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 it increased, a little bit decrease, this is decrease, decrease. So where is the biggest decrease? So you can see it's around this year, so it's gonna be between year 2000 and 2005. Okay, now here, in which year did we have 50% of seniors use alcohol? So this time it has to be on the alcohol. We need to look at 50% of alcohol. So it's gonna be this year, and that is on the year 1995. Okay, so that is how we can use line graphs to make some estimation for our problems. Thank you.